During this module, we'll be discussing Chapter 9, Electrons in Atoms and the Periodic Table. By the end of this chapter, you will be able to understand and explain the key characteristics of the Bohr model of the atom, understand and explain the key characteristic of the quantum mechanical model of the atom. Also, you will write electron configurations and orbital diagrams for atoms. You will identify valence electrons and core electrons. You will write electron configurations for an element based on its position in the periodic table. You also will be able to recognize that the chemical properties of elements are largely determined by the number of valence electrons that they contain. And finally, you will be able to identify and understand periodic trends such as atomic size, ionization energy, and metallic character. On May 6, 1937, while landing in New Jersey on its first transatlantic crossing, the Hindenburg burst into flames, destroying the airship and killing 36 of the 97 passengers. Apparently, as the Hindenburg was landing, leaking hydrogen gas ignited, resulting in an explosion that destroyed the airship. The skin of the Hindenburg, which was constructed of a flammable material, may have also been partially to blame for its demise. The Hindenburg was filled with hydrogen, a reactive and flammable gas. So the question is, what makes hydrogen reactive? Modern blimps are filled with helium, an inert gas. The nucleus of the helium atom has two protons, so the neutral helium atom has two electrons, a highly stable configuration. In this chapter, we'll learn about models that explain the inertness of helium and the reactivity of other elements. And also, we will find the answers for the following questions. What is about helium atoms that makes helium gas inert? By contrast, why is hydrogen so reactive? Elemental hydrogen exists as a diatomic element. Hydrogen atoms are so reactive that they react with each other to form hydrogen molecules. So what is about hydrogen atoms that make them so reactive? Are other elements as reactive as hydrogen? The reactivity exhibited by hydrogen is also seen in other group 1 elements such as lithium and sodium. The inertness of helium is seen in neon, argon, and the other noble gases. Mendeleev's periodic law sums up these observations. When the elements are arranged in order of increasing atomic number, certain sets of properties recur periodically. Models and theories help explain the observed behaviors of groups of elements such as group 1, metals, and noble gases. There are two critical models, the Bohr model and the quantum mechanical model, that propose explanation for the inertness of helium, the reactivity of hydrogen, and the periodic law. This model explains how electrons exist in atoms and how those electrons affect the chemical and physical properties of the elements. Niels Bohr in the left and Erwin Schrödinger in the right, along with Albert Einstein, played a role in the development of quantum mechanics, yet they were bewildered by their own theory of wave-particle duality for the electron. In other words, they said that the electron can behave as a wave as well as a particle. Let's start by talking about the wave behavior, and later we'll talk about the particle behavior. One of the most common type of wave is the light. The interaction of light with atoms helped to shape scientists' models of the atom. Light is a form of electromagnetic radiation. It's also a type of energy that travels through space at a constant speed of 3.0 times 8 power meters per second. And also, the light has properties of both the waves and the particles. When a water surface is disturbed, waves are created that radiative outward from the site. The wave carries energy as it moves through the water. So let's talk about some characteristic of the light. First of all, the wavelength. The wavelength of a light, also known as lambda, this is the symbol, okay, for lambda, is defined as the distance between adjacent wave crests. Here we have a wave, and you can see this adjacent wave crest from here to here. So the distance between here and here is the wavelength, as well as if you measure the distance between this crest and this crest, okay, also this will be the wavelength, or from here to here, okay, that's a complete cycle, okay, so that's the measure from crest to crest of a wavelength. From here to here is the wavelength, or here to here, or here to here. Okay, so that's a complete wavelength for uh, any wave. White light, as produced by the sun or by a light bulb, contains a spectrum of wavelengths and therefore a spectrum of color. We see these colors: red, orange, yellow, green, blue, indigo, and violet in a rainbow, or when white light is passed through a prism. The red light, with a wavelength of 750 nanometers, has the longest wavelength of visibility light. On the other hand, the violet light, with a wavelength of 400 nanometer, has the shortest wavelength of the visible light. So we can see here that the red one has a 750 nanometer, that's a larger wavelength than the one for the reported for the violet, that is 400 nanometers. 1 nanometer is equal to 1 times 10 power of minus 9 meter. The presence of color in white light is responsible for the colors that we see in our everyday vision. When a light passes through a prism, this is what we see: a rainbow, which is really the constituent colors of the light. So why is this behavior? As we see in the previous slide, each color has a specific wavelength. Because different wavelengths or color of light travel through a medium at different speed, the amount of bending is different for different wavelengths. Violet is bent the most and red the least, because violet light has a shorter wavelength, and short wavelengths travel more slowly through a medium than longer ones do. So because white light is made up of all visible wavelength, its colors can be separated or dispersed. This is known also as dispersion, by this difference in behavior. So because each of this color has its specific wavelength, the specific wavelength will travel in a different speed inside a medium, so that will make this difference in the bend. Okay, so the purple, the violet, has the most bend because it's the ones that travel slower in that medium. Here we have a girl with a red shirt, and the red is because the shirt reflects the red light. The shirt absorbs all of the other colors of light except the red light. Our eyes will see only the reflected light, making the shirt appear to be red. Another characteristic of wave is the frequency. The frequency of a light, also known as the nu, this is basically the symbol like a V, is defined as the number of cycles or crest that pass through a stationary point in 1 second. Wavelength and frequency are inversely related. The shorter the wavelength, the higher the frequency. Here we have a wave with long wavelength, so that means that this wave has a lower frequency. Okay, so from here, let's assume that from this point to this point, we have 1 second. Okay, so this is the behavior of this long wavelength. Okay, in a range of 1 second. From the crest to crest, as we mentioned before, you have a cycle. Okay, so from here, we can see that we have 1, 2, and 3 cycles basically in 1 second. Okay, or we can count also from this point to this point. We have 1, we have 2, and we have 3.5 cycle. Okay, so for this long wavelength, we have 3.5 cycles. Now, what happened with a short wavelength? Okay, a wave that had a short wavelength. So we can see that from here, and also this is the same frame time, it's 1 second. So we have 1, we have 2, 3, 4, 5.5. So in 1 second, you have 5.5 cycles. You are more frequently. So with shorter wavelength, you have a high frequency, and with long wavelength, you have a low frequency. These are the wave characteristic of the light. So let's talk now about the particle characteristic for the light. Light can be viewed as a stream of particles. A particle of light is called a photon. We can think of a photon as a single packet of light energy. The amount of energy carried in the packet depends on the wavelength of the light. The shorter the wavelength, the greater the energy. Or in other words, also about the frequency, as a higher frequency, higher the energy, because remember that the wavelength and the frequency, they are inversely related. Light waves carry more energy if their crests are closer together, with higher frequency and shorter wavelength. Violet light, that is the shorter wavelength, carries more energy per photon than the red light, the longer wavelength. So that means that the violet light has a higher energy than the red light. So the electromagnetic radiation is a form of energy that travels through space at a constant speed of 3.0 times power of 8 meters per second, and can exhibit wave-like or particle-like properties. The wavelength of electromagnetic radiation determines the amount of energy carried by one of its photons. The shorter the wavelength, the greater the energy of each photon. The frequency and energy of electromagnetic radiation are inversely related to its wavelength. Okay, so frequency and energy are directly related. So if you have a higher frequency, you have higher energy. Okay, but this one will be for shorter wavelength, because those are inversely related. So with a larger wavelength, you have lower energy. The frequency, basically, I mentioned this. Here we have the whole electromagnetic spectrum. On the left side, we have the radiation right here with the longest wavelength but lower frequency. So that means also that we have the lower energy. Okay, while in the right hand of the spectrum, you will find the radiation with shorter wavelength but also with higher frequency as well as higher energy. Close to the middle of the whole electromagnetic spectrum, we will find the visible region. So let's go through each of the regions of the electromagnetic spectrum: the radio waves, infrared, X-ray, gamma rays, and visible light. Let's start first with the gamma rays. The shortest wavelength and most energetic photons are the gamma rays. The gamma rays are produced by the sun, by stars, and by certain unstable atomic nuclei on the Earth. Excessive human exposure to gamma rays is dangerous because the high energy of gamma ray photons can damage biological molecules. The second region is the X-rays radiation with longer wavelength and lower energy than the gamma rays. These are familiar to us from their medical use. X-ray pass through many substances that blocks visible light and are used to image internal bones and organs. Like gamma ray photons, X-ray photons carry enough energy to damage biological molecules. While several yearly exposures to X-rays are relatively harmless, excessive exposure to X-rays increases cancer risk. Between X-rays and visible light in the electromagnetic spectrum is the ultraviolet or UV light, familiar to us as a component of sunlight that produces sunburn or suntan. While not as energetic as gamma ray or X ray photons, ultraviolet photons still carry enough energy to damage biological molecules. Excessive exposure to ultraviolet light increases the risk of skin cancer and cataracts and cause premature wrinkling of the skin. Next on the spectrum is the visible light, ranging from the violet, which is the shorter wavelength with higher energy, to the red, has the longer wavelength and lower energy. Photons of visible light do not damage biological molecules. Photons of visible light do cause molecules in your eyes to rearrange, which sends a signal to our brains that results in vision. The next one is the infrared light, with even longer wavelength than visible light. The heat you feel when you place your hand near a hot object is infrared light. All warm objects, including human bodies, emit infrared light. While infrared light is invisible to our eyes, infrared sensors can detect it and are often used in night vision technology to see in the dark. In the infrared region of the spectrum, warm objects such as human bodies glow, much as a light bulb glows in the visible region of the spectrum. Here we can see a normal picture of a guy with his dogs. And here we can see the infrared photograph. So the warmest areas appear as red and the coolest as dark blue. Have you ever heard about that healthy dogs have cold noses? Here you have the evidence. As you can see, the nose hairs are in blue. So that means that they are cooler than the red of the body. Beyond infrared light, at longer wavelengths still are the microwaves, used for radar and microwave ovens. The microwave light has longer wavelengths and therefore lower energy per photon than visible or infrared light. The microwave light is efficiently absorbed by water and can heat substances that contain water. Substances that contain water, such as food, are warmed by the radiation of a microwave oven, but substances that do not contain water, such as a plate, are not. Some types of dishes contain substances that absorb microwave radiation, but most do not. And finally, the longest wavelengths of light are the radio waves, which are used to transmit the signals used by AM and FM radio, cellular telephones, television, and other forms of communication. Some of this radiation has been used for treatment against diseases. X rays and gamma rays are sometimes called ionization radiation because the high energy in their photons can ionize atoms and molecules. When ionizing radiation interacts with biological molecules, it can permanently change or even destroy them. Doctors can use ionization radiation to destroy molecules within unwanted cells, such as cancer cells. In the radiation therapy, doctors aim X rays or gamma ray beams at cancerous tumors. The ionization radiation damage the molecules within the tumor's cells that carry genetic information, and the cell dies or stops dividing. Healthy cells often inadvertently sustain damage during treatments, resulting in side effects such as fatigue, skin lesions, and hair loss. Doctors try to minimize the exposure of healthy cells by appropriate shielding and by targeting the tumor from multiple directions, minimizing the exposure of healthy cells while maximizing the exposure of cancerous cells. The elements have the ability to absorb energy in the form of heat, light, or electricity. This is known as absorption. It often re-emit the energy as light, frequently known as emission. This absorption and emission of light by atoms is due to the interaction of the light with the electron in the atoms. If the atoms in the tube are different, the electrons have different energies and the emitted light is a different color. Here we have neon, which you can find it inside a glass tube where it absorbs electrical energy. So that's the absorption part. It absorbs that electrical energy and then re-emit the energy as a red light. So the emission is in the red light form. Let's show you two more examples. For example, light emitted from a mercury lamp here in left is blue, while the emission for hydrogen is pink. Okay, those atoms, in the left we have mercury, and in the right we have the hydrogen. They would absorb energy, and then they will re-emit that energy. Okay, in different colors. For the mercury will be in blue, and for the hydrogen will be in pink. Previously, we showed that the electromagnetic spectrum is continuous. However, the emission spectra of an element is non-continuous. A white light spectrum, as we mentioned, is continuous, with some radiation emitted at every wavelength. So you can see the whole spectrum, okay, starting from red and by the end of the purple or violet. However, the emission spectrum of an individual element includes only certain specific wavelengths. So you're not going to see a spectrum like this, okay, for specific elements. You will see something maybe like this. Instead of the whole colors, you will see just line with specific wavelengths. Okay, this is the case for hydrogen. The light of hydrogen will emit just this specific four wavelength. The same thing with helium. This is the spectrum for the helium light. So it's not like a continuous, okay, it's a not continuous spectrum. As well for the neon. The neon light has much more different wavelength, but still is a non-continuous spectrum. If you use a prism to try to see the components of the light emitted by hydrogen, you'll see a non-continuous spectrum, as we can see here. Okay, we have here the source, okay, of the hydrogen light. Okay, go through the prism, and you can see before, when it was a white light, we saw all the spectrum here. But now, because of hydrogen, is hydrogen the source of that light, we can see just a few of those wavelengths. The same thing is going to happen with any other element, and you'll see a non-continuous spectra with distinct wavelengths for that element. So the question is, why do atoms, when excited with energy, emit light only at a particular wavelength? To try to answer this question, and also this one, why do they not emit a continuous spectrum? To try to answer this question, we are going to introduce a simple model developed by Niels Bohr called the Bohr model. In this model, electrons travel around the nucleus in circular orbits that are similar to planetary orbits around the Sun. However, unlike planets revolving around the Sun, electrons in Bohr model can orbit only at specific fixed distance from the nucleus. So this distance from the nucleus to the first orbit has a specific distance as well to orbit 2, 3, 4, and 5. Okay, this is the Bohr model. The energy of each Bohr orbit specified by a quantum number n equals to 1, 2, or 3 is fixed or quantified. Bohr orbits are like steps of a ladder, each at a specific distance from the nucleus and each at a specific energy. It is impossible for an electron to exist between orbits in the Bohr model. So you can find an electron in the n equals to 1, n equals to 2, n equals to 3, 4, 5, 6, etc. You can find an electron in the middle of those orbits. Okay, all of the electrons will be the electrons. If you find some of them, will be in a specific orbit that has specific distance and energy associated with it. When a hydrogen atom absorbs energy, an electron is excited to a higher energy orbit. So here we have the energy absorption. This is the light that will excite this electron, okay? And because it has a lot of energy now, it will jump to another orbit, okay? Now, the electron then relaxes back to a lower energy orbit, emitting a photon of light. So once he reached this orbit, for example, it will release that energy in form of light so we can go back to the lower orbit. Okay, so this light emission has a specific wavelength. That is the energy associated with this transition from this orbit to this orbit. Okay, now it is important to understand that we have a specific energy that is the one that will excite this electron, and we can have sometimes, really rarely, have the same wavelength of the same or the same energy, okay, as the one that was absorbed. But most of the time, that light emission, the energy associated with this light emission is going to be lower than the energy that it was used to excite that electron. Okay, so we're going to have a different wavelength as an emission as the one that was absorbed. Since the amount of energy in a photon is directly related to its wavelength, the photon has a specific wavelength. The light emitted by excited atoms consists of specific lines at specific wavelengths, each corresponding to a specific transition between two orbits. For example, the line at 486 nanometer in the hydrogen emission spectrum correspond to an electron relaxing from the orbit n equals to 4 to the orbit n equals to 2. Okay, so that's the wavelength, okay, that you will see when this transition occur from n4 to n2. So what do you expect if the transition was from 3 to 2? It will have a higher or a lower wavelength. When we have a transition from 3 to 2, we have less energy. So because it's a lower energy, it will have a longer wavelength. Okay, so in the line of 657, that is another one of the line that we can see for hydrogen nanometers, correspond to an electron relaxing, okay, from the n equals to 3 orbit to n equals to 2. Okay, so from 3 to 2, you have uh, a smaller amount of energy than from a transition from 4 to 2. That's why, because you have a lower amount of energy in this transition, this will represent a higher or longer wavelength as compared to a transition from orbit 4 to orbit 2. Here is a representation of those emissions lines for hydrogen, okay? So when you go from 3 to 2, you can see here these arrows basically represent energy. So because this transition has a lower energy, it will have a longer wavelength. While this one that has this transition has a higher energy transition, okay, this emission, because you're going from an orbit, a higher orbit to a lower orbit. This one has a higher energy associated with this emission, so that's why it has a lower frequency as compared, for example, to the red. And this blue-green one that is in 486 is in the middle because it has uh, a release, okay, this amount of energy that is higher than this one but lower than this one. So that's why basically it's between those two transitions. Okay, so those wavelengths are associated to a specific amount of energy release, okay, when you goes from a higher orbit to a lower orbit. The great success of the Bohr model of the atom was that it predicted the lines of the hydrogen emission spectrum. However, it failed to predict the emission spectra of other elements that contain more than one electron. For this and other reasons, the Bohr model was replaced with a more sophisticated model called the quantum mechanical or the wave mechanical model. The quantum mechanical model of the atom replaced the Bohr model in the early 20th century. In the quantum mechanical model, Bohr orbits are replaced with quantum mechanical orbitals. So now we're going to talk about orbital, but it's basically represent the same as the orbits. Orbitals are different from orbits in that they represent probability maps that show a statistical distribution of where the electron is likely to be found. Quantum mechanics revolutionized physics and chemistry because in the quantum mechanical model, electrons do not behave like particles flying through space. We cannot, in general, describe their exact paths. An orbital is a probability map that shows where the electron is likely to be found when the atom is probed. It does not represent the exact path that an electron takes as it travels to space. So let's see how baseball can help us to understand this concept. Imagine a baseball thrown from the pitcher's mound to a catcher at home plate. The baseball's path can easily be traced as it travels from the pitcher to the catcher. In the quantum mechanical world of the electron, the catcher could not know exactly where the electron would cross the plate for any given throw. He would have no way of putting his mitt in the right place to catch it. However, if the catcher kept track of hundreds of electron throws, he could observe a reproducible statistical pattern of where the electron crosses the plate. He could even draw maps in the strike zone showing the probability of an electron crossing a certain area. These maps are called probability maps. Here we have an example. of that probability maps. Okay, so as you get closer to here, you have a higher probability to find the electron, and also here and also in the outer shell. So to describe the behavior of a pitch electron, you would have to construct a probability map of where it would cross the home plate. Let me introduce some concepts that will be useful on quantum mechanical models. In the quantum mechanical model, a number and a letter specify an orbital or orbitals. The lowest energy orbital in the quantum mechanical model is called the 1s orbital. It is specified by the number 1 and the letter s. The number is called the principal quantum number, or the letter n, and specifies the principal shell of the orbital. Okay, so that's the meaning of the number. It tells us the principal shell of the orbital, and also is known as principal quantum number. The single electron of an undisturbed hydrogen atom at the room temperature is in the 1s orbital. This is called the ground state, or lowest energy state of the hydrogen atom. Now, we talk about that those electrons could absorb energy. So the absorption of energy by a hydrogen atom can cause the electron to jump or make a transition from the 1s orbital to a higher energy orbital. When the electron is in a higher energy orbital, the hydrogen atom is said to be in an excited state. All the atoms of each element have one ground state and many excited states. The higher the principal quantum number, the higher the energy of the orbital. So here we have a representation of energy increasing from the lowest to the higher number of the principal quantum number. So as higher you are, okay, you're going to have more energy. The possible principal quantum numbers are n equals to 1, 2, and 3, with energy increasing as n increases. Since the 1s orbital has the lowest possible principal quantum number, it is in the lowest energy shell and has the lowest possible energy. Now, what the letter of the orbital means. The letter indicates the subshell of the orbital and specify its shape. The possible letters are S, P, D, and F, each with a different shape. Orbitals with the S subshell have a spherical shape. Orbitals are sometimes represented by dots, where the dot density is proportional to the probability of finding the electron. The dot density for the 1s orbital is greatest near the nucleus and decreases farther away from the nucleus. I will show you an example of this in a few minutes. The electron is more likely to be found close to the nucleus than far away from it in a 1s orbital. Orbitals can be represented as geometric shapes that encompass most of the volume where the electron is likely to be found. The 1s orbital can be represented as a sphere that encompasses the volume within which the electron is found 90% of the time. If we superimpose the dot representation of the 1s orbital on the shape representation, we can see that most of the dots are within the shape sphere, meaning that the electron is most likely to be found within the sphere when it is in the 1s orbital. The dot density and shape representation of the 1s orbital here we have the dot density that is proportional to the probability of finding the electron. This one represent the is the dot representation. Okay, so we can see here that as close you are to the nucleus, you will find a higher probability. The greater dot density near the middle represent the higher probability. Okay, so this one is the shape representation, and here is when we superimposed, okay, both of them. And as I mentioned before, you have a 90% probability to find the electron in this area. So the number of a subshell in a given principal shell is equal to the value of n. So that means that if we have the principal number 1, okay, we're going to have one subshell, that is the s. So that's why we find the 1s. For the N2 principal shell, we will have two subshells, the S and the P. For a principal shell of 3, we're going to have three subshells, the S, the P, and the D. So we're going to find a 3S, 3P, and 3D. We will never find a 1P or 1D, okay, because in the shell number 1, we're going to find just one subshell, that is the S. The same thing with the shell number 2. We will never find a 2D, okay, because we just have two subshells that are the S and the P. So what about if we are in shell number 4, okay, with a principal quantum number of 4, how many subshells we will have? Also 4. It will be S, P, D, and F. And that's the same way with it. We will never see a 3F because we just have three subshells that are the SPD for the quantum principal number of 3. The s subshell contains the 2s orbital with higher energy than the 1s orbital and slightly larger but otherwise similar in shape. Okay, so the 1s orbital is going to have a sphere shape as well as the 2s, but the 2s is going to have a higher energy than the 1s, and also it will be slightly larger, okay, than a 1s orbital. The p subshell contains three 2p orbital, all with the same dumbbell-like shape, but with different orientation. So when we have the s, we're going to have just one s. When we're going to be in the p, we're going to have 1, 2, 3 subshells that represent the p orbitals. One will be, as we can see here, this is the dot representation, okay? Also here and here, we have a higher probability to find the electron in these regions, okay? So here we have the x and the x-axis. We have another one in the y-axis and another orbital subshell p in the z axis. The next principal shell, that is n equals to 3, contains three subshells specified by s, p, and d. The s and p subshells contain the 3s and the 3p orbitals, similar in shape to the 2s and the 2p orbitals, but slightly larger and higher in energy. Okay, and remember that we're going to have just one 3s and three 3p orbitals. Okay, so when in the two principal shell, we have the 2s, one 2s, and three 2p. Now, with that we are in 3, we're going to have the 3s, the 3p, and also we're going to find the d subshell that will contain 5 d orbitals. So here we have a representation of the 5 different shapes for the d orbitals, okay, and their orientation in space. So we have the dyz, the dxy, the dxz, and also the dx2 minus g2, y2, and also the dz2. So these are the 5 different representation for the 5 orbitals of the 3D. The quantum mechanical model predicts the bright line spectrum of hydrogen as well as the Bohr model does. But also the quantum mechanical model can predict the bright line spectra of other elements, and the Bohr model cannot predict spectra for atoms with more than one electron. The Bohr model, as we mentioned before, was replaced with a more sophisticated model called the quantum mechanical or wave mechanical model. The Bohr model is still important because it provides a logical foundation to the quantum mechanical model and reveals the historical development of scientific understanding. Now it's time to learn how the electrons are distributed on the atom using the quantum mechanical model. An electron configuration shows the occupation of orbitals by electrons for a particular atom. The electron configuration for a ground state hydrogen atom is as follows: 1s1, 1s that represent the orbital, and the exponent here represent the number of electrons in that orbital. So the electron configuration tells us that hydrogen's single electron is in the 1s orbital. Another way to represent this information is with an orbital diagram, which gives similar information but shows the electrons as arrows in a box representing the orbital. The orbital diagram for a ground state hydrogen atom is as follows. So here we have the orbital 1s with just the one electron that hydrogen has. The box represents the 1s orbital, and the arrow within the box represents the electron in the 1s orbital for hydrogen. In orbital diagrams, the direction of the arrow pointing up or pointing down represents the electron spin, a fundamental property of the electrons. The Pauli exclusion principle states that orbitals may hold no more than two electrons with opposing spins. We symbolize this as the two arrows pointing in opposite directions. So if we need to put two electrons in the same orbital, we can use this type of arrow, but remember that they need to be pointing in opposite direction, one up and one down. Usually the first one goes up and the second one goes down, but if you want to write the first one pointing down and the second pointing up, it's okay. The important thing is that they need to be pointing in opposite direction. So, in a multi-electron atoms, the subshells within a principal shell do not have the same energy because of electron-electron interactions. Different subshells within the same principal shell have different energies. Sometimes subshells with higher principal quantum number will have a lower energy than a subshell with a smaller principal quantum number. For example, the 4s subshell is lower in energy than the 3d subshell, even though its principal quantum number for the 4s is higher than the 3d. Here we can see the representation of the energy ordering for the orbitals. Here we can see that the difference on energy between subshells and also the overlapping of some subshells. So as we expected, the 1s has a lower energy than the 2s than the 2p, the 2p a lower energy than the 3s a lower energy than the 3p, but instead of the 3d, the next one with the higher energy is the 4s. So that means that the 4s has a lower energy than the 3d. The same thing happens with the 5s. Instead of going from the 4p to the 4d, we need to go from the 4p to the 5s. This to when we are filling the subshells. So when you go from 4p, you're not going directly to 4d. You're going to 5s. Okay, so to fill the orbitals, you will start with the lowest energy orbital available. Okay, and since we know that only two electrons are allowed in each orbital. So let's do the electronic configuration for some elements. Helium atom has 2 electrons. The electron configuration and orbital diagram for helium are as follows. So the first orbital that we have is the 1s, and each one we can put just 2 electrons. So that means that we have the 1s2. Okay, remember that these two represent the number of electrons, and we can put no more than 2 electrons in each of the subshells. That's why the orbital diagram, this is the electronic configuration, this is the orbital diagram, is 1s with 2 electrons in this box, one pointing to up and the other one pointing down. So what about lithium? Lithium atom has 3 electrons. So that means that we start with the 1s where you can put just 2 electrons. So it's going to be 1s2. And the next one is going to be the 2s. So we have just one left because we're 3 electrons. 3 minus 2, that we have 2 here in the 1s2. It means that we have just 1 electron to put here in the 2s subshell. So we have the orbital diagram. We have 2 electrons in the 1s and 1 electron in the 2s. So here we have the 3 electrons of the atom of lithium. Now, what happened with carbon? Carbon has 6 electrons. So the electron configuration is as follows. We start with the 1s2, okay, 2s2. Now we can fill this next orbital. And now with the p, remember that when we are talking with the p, we have 3 subshells that are 2p. Okay, so that means that in the 2p, we have a maximum space to be filled with 6 electrons. Okay, so we have 6 available positions or space to put electrons when we're talking about the p's, because each subshell p gonna have 2 electrons. Okay, space for 2 electrons, and because we have 3 of them, we can we have the ability to put 6 electrons in the 2p. So the 2p electrons occupy the p orbitals of equal energy singly rather than pairing in one orbital. So this is really important, okay? This is known as the Hund's rule. When filling orbitals of equal energy, electrons fill them singly first with parallel spin. So here we have the opportunity to put in the 2p, we have, as I mentioned before, 6 possible places to put the electrons, because remember that in each box we can put 2 electrons. So we have 3 boxes available, so we can have a maximum of 6 electrons here. Now, when we're going to put the electron, we're going to fill those orbitals, because these 3 subshells have the same energy, we need to put each electron individually first, okay? And then when we don't have any more space, we can pair them, okay? But if we have a space available, we need to put them as single electrons, okay? With parallel spins, all of them pointing up or all of them pointing down. So basically this is a template, okay, for to know how to fill the orbitals, starting with the 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. So you can learn this, or also you can find out a way to draw like a ladder, okay, and then establish this order, okay, to fill those electrons and create that electronic configuration for each of the elements. So to write an electronic configuration, first we need to fill the lower energy orbitals before the higher energy orbitals. The orbitals can hold no more than 2 electrons each. When 2 electrons occupy the same orbital, remember, they must have opposite spins. This is known as the Pauli exclusion principle. When orbitals are identical energy are available, for example, the p, we have 3p, or the d, we have 5ds, all of these are first occupied singly by electrons with parallel spins rather than electrons in pairs. This is known as the Hund's rule. So, For nitrogen, nitrogen has 7 electrons, okay? So that means that we have 1s2, 2s2, we have 4 here, okay? So now we need to fill the next orbital. We have 3 electrons available to fill all orbitals. The next one, it will be the 2p, and remember that we have 3, okay, of this p subshells, so we can put 1 in each of them, and this will be basically the representation for the electronic configuration of nitrogen. So what about oxygen? Oxygen has 8. So that means that now, because we don't have any more space here available to add one more electron, now we can pair it. And remember that needs to be in opposite uh, direction, okay, as the one that was before. So now we have 1s2, 2s2, 2p, 4. Okay, this is basically the electronic configuration for oxygen. And for fluor, fluor has 9 electrons, so that means that we need to put that ninth electron where? In pair with this one, okay? So that's why we have here the configuration of fluor. Okay, so fluor here we have 8 and 1 9 electron, 1s2, 2s2, 2p5. And finally for neon that has 10 electrons, now we can fill all this subshells, 1s2, 2s2, and 2p6. So we don't have any more space in the 2p for the next element, okay, to put that electron. So we need to move to the 3s in that case. When writing electron configuration for elements beyond neon or beyond any other noble gas, the electron configuration of the previous noble gas can be abbreviated by the symbol of the noble gas in brackets. So that means that we have sodium. As I mentioned before, the sodium will have the electron configuration of 1s2, 2s2, 2p6, and 3s1. Okay, remember that we filled this p orbital, okay, with the 6 electrons. So now we need to move on to the next subshell available, that is a 3s1. But this, all of this is the electronic configuration of neon that is a noble gas. So we can substitute all of this, okay, for the symbol of neon inside a bracket, and then we can put the other orbitals that are not associated with this configuration of the noble gas. So we can do that for all of the electrons, the elements that are beyond a noble gas. We can use the symbol of that noble gas with brackets and also the others orbitals that are associated with the element that we want trying to draw the electronic configuration. So the valence electrons are the electrons in the outermost principal shell. The principal shell with the highest principal quantum number n. These electrons are important because they are involved in chemical bonding. So even though you have a lot of electrons in an atom, just the ones that are valence electrons are the ones that are involved in chemical bonding. The electrons that are not in the outermost principal shell are called the core electrons. So those electrons that are part of the core electrons, they are not involved neither in chemical bonding. The ones that are involved in the chemical bonding are the electrons of the valence electron or the electrons that are in the outermost principal shell. Let's see an example. Silicon has 4 valence electrons, those in the n equals to 3 principal shell, and 10 core electrons. So here we have the electronic configuration for silicon. Also, we can abbreviate this by using the configuration of neon here, okay, and the 3s2, 3p2. But for now, we just write the whole electronic configuration to show you that these ones in blue are the core electrons. These are not involved in chemical bonding, but they are in the atom, and these electrons here that are in the outermost shell, these are known as the valence electrons. So you have the core electrons and the valence electron, the ones that are associated with electron with chemical bonding. Selenium, another example here, has 6 valence electrons. Okay, so here we have uh, the 4. Remember that the valence electrons are the ones that are in the outermost shell. So even though in the order we write first the 4s2 and the 3d10, remember that this is not the only electrons that are in the subshell 4, or on the in the principal number 4. We also have 2 electrons here, so that means that we have a total of 6 valence electrons. Okay, even though we fill this first than the 3d10. Okay, and that's why maybe you sometimes will be said, no, we had just 4 electrons. But remember that all the electrons are in the outermost shell. In this case, the outermost shell is number 4. So how many electrons we have in that level of number 4? We have 2 and 4, 6 valence electrons. And the other ones are the core electron. This one that is between these two, this is not part of the valence electron because these 10 electrons are in the principal number 3 and the orbital 3. Okay, so that means that we have just 6 of them in the outermost principal shell. So all other electrons, including those in the 3D orbitals, are core electrons. The elements within a column of a periodic table all have the same number of valence electrons and similar outer electron configuration. As we can see here, in the 1A, all of them are 1s1, 2s1, 3s1, so they have basically the same similar outer electron configuration, but the only thing that they change is the principal number because they have are in higher orbital energies. The same thing happens with the 2A. The 2A has a 2s2, the 3s2. The 3A, 2s2, 2p1, 3s2, 3p1. Okay, and the same thing happened with each of the different groups or families. In other words, this is one of the patterns that exist for the entire periodic table. For example, the first 2 columns on the left side of the periodic table are the S block. The 6 columns on the right side of the periodic table are the P block. The transition metals are the D block, and the lanthanides and actinides are also called the inner transition metals, are the F block. So here we have the periodic table and the 4 blocks. Here we have, as we mentioned, from the family 1 and 2, the S block. Okay, from family 3 to 8, we have the P block. Here in the middle, the transition metals, they are known as the D block elements, and the lanthanides and the actinides, the F blocks. Okay, because from there they start to use the F orbitals. This one starts to use the D, this one the P, and this one the S. So that's why they receive those names: the S block, the P block, the D block, and the F block. So let's talk about the periodic trends in the electron configurations of the main group elements. The number of valence electrons for any main group element is equal to the group number of its column, with the exception of helium. Chlorine has 7 valence electrons because it is in the column with the group number 7A. The row number in the periodic table is equal to the number of the highest principal shell, or the N value. Chlorine is in row 3. Its highest principal shell is the N equal to 3 shell. Remember that main group elements are those in the far left column, 1A and 2A, and the 6 far right columns of the periodic table, from 3A to 8A. What about the periodic trends in the electrons configuration for the transition group elements? The transition elements of the transition metal have electron configuration with trends that differ somewhat from main group elements. The principal quantum number of the d orbital being filled across each row in the transition series is equal to the row number minus 1. So for the first transition series, the order configuration is 4s2 3dx, where x is the number of the electrons. Two exceptions we have is going to be chromium, with that is 4s1 3d5 instead of 4s2 3d4, and copper, that is 4s1 3d10 instead of 4s2 and 3d9. I'm going to show you this in the next slide. These exceptions occur because a half-filled d subshell and a completely filled d subshell that are particularly stable. Okay, so what I'm saying is that here we have chromium. Okay, and you expect that vanadium here is 4s2 3d3, that the next element, its electronic configuration will be 4s2 3d4. But one of those electrons of the 3d4 will, of the 3d, 3d4 will move to one of the 4s2 to the 3d4, so you can have the 3d5 and you have the 4s1. This will give a high stability, okay, for that configuration. The same thing happened with copper. Here we have, instead of 4s2 3d9, you expected that to be the configuration for copper, 4s2 3d9. What happens is that one of the electron of 4s will move to the 3d9 to complete, okay, that shell, and that will give a lot of stability, and you will have the 4s half a field that also has a higher stability. Okay, so that's why we have these two exceptions here. Okay, and also for this, basically the one in the bottom below them, okay, is basically because of that. So you can feel those um, those orbitals, okay, in a way that the element gains stability. So that's why you have those two exceptions in the 4 period. The number of outer shell electrons in a transition series does not change as you move across a period. The transition series represents the filling of core orbitals, and the number of outer shell electron is mostly constant, either 2 or 1. So we have here that for 2 electrons is going to be 4s2 3dx is going to be dependent on which element is. The same thing happened with when we have the 4s1. Okay, so we have just one electron in the outer shell, and we have different number 5 or 10 in the core shell. So the same thing here. Okay, so we have basically you can see that here for this period the um, the principal number is 4, and the 4 does not change. Okay, the 4s is basically you have the same 4s, 4s2 most of them, and here for chromium and copper 4s1 because of the exception that I mentioned before. The same thing happened in this period. Okay, 5s2 5s2 5s1, the same 5s1 5f2 5f2 so you have that it doesn't change as here you can see you have 5s2 5p1 5s2, 5p2, 5s2, 5p3. So in the transition metals, you're not changing, okay, those electrons in the outermost shell, okay, as happened here with the main groups. In the main groups, you are changing that from 4s1 to 4s2, from 6s1 to 6s2, from 6s2 6p2 to 6s2 6p3. You're adding electrons to that outermost shell. Here not. You're not changing those number of electrons. Most of the time are 2 or just 1 electron in the transition series, for the elements in the transition series. We can see that the organization of the periodic table allows us to write the electron configuration for any element based simply on its position in the periodic table. For example, suppose we want to write the electronic configuration of P, phosphorus. The inner electrons of phosphorus are those of the noble gas that precede the phosphorus. So here we have phosphorus. The noble gas before phosphorus is neon. So this one has all the inner electron configuration for phosphorus. So we can represent the inner electron with the symbol of neon in bracket. We obtain the outer electron configuration by tracing the elements between the neon and the phosphorus. So from here to here, we need to trace what is the configuration to determine the electronic configuration for phosphorus of the outer electrons. Okay, so remember that the highest n value is given by the row number. So here we are in the 3. So that means that we go through the S block. So we have the 3s2, okay? And then we go through this first 3 of the P block. So 1, 2, 3 is 3p3, okay? So we pass through 2 of the S block, okay? 3s1, 3s2, and also 3p1, 3p2, 3p3. So that means that the electronic configuration for phosphorus will be neon in bracket, okay, 3s2, and then 3p3. And that's the electronic configuration for phosphorus, okay? The same thing with any of the other elements, okay, um, for any element. And here we need to remember that we go through the D blocks, and the D blocks are uh, one principal number before, okay, the row that he has. So here we have the 4D, okay, here in the 5s2, then will be the 4d10, and whatever number we want to determine here in the P block. Okay, the same thing here. For this one, we have the 6s2 and the 5d10 if we are going to use the whole thing, okay, 5d10. And then we go here again to the 6p. Remember that these are going to be one before the S and the P. So here we have 4s, 4p, and here the 3ds. So 4s2, 3d10, and 4px, the number of the element that you are looking for. So we can write the electron configuration for any element based on its position in the periodic table. The inner electron configuration is the electron configuration of the noble gas that immediately precedes the element in the periodic table. Represent the inner configuration with the symbol of for the noble gas in brackets. The order electrons can be determined from the element's position with a particular block, S, P, D, or F, in the periodic table. Trace the elements between the preceding noble gas and the element of interest and assign electrons to the appropriate orbitals. The highest principal quantum number, highest n value, is equal to the row number of the element in the periodic table. And remember that for any element containing d electrons, the principal quantum number of the outermost d electron is equal to the row number of the element minus 1. So as we are in the 4s, in the 4 row, it's going to be 4s, 3d, and then 4p. Okay, as I mentioned before. The quantum mechanical model allows us to understand and explain different elements' trends. For example, why sodium tends to form sodium ions and fluorine tends to form F minus ions. Why some elements are metals and others are nonmetals. Why the noble gases are chemically inert and the alkali metals are chemically reactive. Also, that chemical properties of elements are largely determined by the number of valence electrons that they contain, and the properties vary in a periodic fashion because the number of valence electrons is periodic. So let's start with the noble gases, which are in group 8A. Calculations shows that atoms with 8 valence electrons, or 2 for helium, are predicted to be particularly low in energy and therefore stable. So all the elements that are part of the noble gases, they are really, really stable. That's why all of the other elements wants to be like them, because they want to have the stability that the noble gas have. The noble gases are chemically stable and thus relatively inert or non-reactive, as accounted for by the quantum model. Elements with electron configuration close to the noble gases are the most reactive because they can attain noble gas electrons configuration by losing or gaining a small number of electrons. That's why they are really, really reactive, because they want to lose those electrons pretty fast or gain those electrons fast to have the same electronic configuration as the noble gases. The next group is the alkali metals. Alkali metals, group 1, are among the most reactive metals since their order electron configuration NS1 is one electron beyond a noble gas configuration. So they have two options. They can they can give that electron, or they can gain or receive 7 electrons. So I think it's more easy to give that 1 electron. So if they can react to lose the electron, they attain a noble gas configuration. This is why the group 1 metals tends to form cation with a charge of 1 plus, because for them it's really easy to remove that electron to gain the noble electronic configuration of the noble gas. Okay, and that in that way they will be really, really stable. The alkaline earth metals, they are of the group number 2, all have electron configuration of ns2, and therefore 2 electrons beyond a noble gas configuration. In their reaction, they tend to lose 2 electrons, forming a 2 plus ions and attaining a noble gas configuration. So as the same way as the group 1, for them it's more easy to lose those 2 electrons than look for 6 to have 8 and be and have the same electronic configuration of the next noble gas, okay, in the same period. So for them it's more easy to lose those 2 electrons. So if you're neutral and you lose 2 negative charges, you will have now an ion with a 2 positive charge, a cation with a 2 positive charge. The halogens is in group 7, all have ns2 and p5 electron configuration and are therefore 1 electron short of a noble gas configuration. They have 7 electrons or valence electrons, so they just need to add 1 more electron to have the noble gas configuration. In their reaction, halogens tends to gain 1 electron, forming an ion with a charge of 1 minus. Because they were neutral, so they are gaining this electron, so they could have 8 electrons and have the same configuration of the next noble gas. Okay, so in that way, that's why all the ions from family 7 that are produced are with a charge of 1 minus. So here we have basically the periodic table, but with the most predictable ions. Okay, so for family 1, most of them are going to be +1, family 2, 2 plus, family 3, 3 plus, family 7, 1 minus, family 6, 2 minus, because remember they have 6 valence electrons, so they want to have 8 to have the same number of valence electrons as the noble gas, so they will need to gain or receive 2 electrons. So if they are neutral, when they receive 2 negative charge, they will be turned on an ion with a 2 minus charge. And with family 5, basically the ion that they form is the nitrogen with a -3 charge. Those are the most common ions in the main groups that we produce in the main groups. There is another trend that you can find in the periodic table, and this one is the atomic size, which depends on 2 factors. Factor number 1 is as you move to the right across a period in the periodic table, atomic size decreases. Okay, so the atomic size decreases when you're moving from left to right in across a period. The atomic size of an atom is determined by the distance between the outermost electrons and the nucleus. The size of an orbital depends on the principal quantum number, which with each step across the period, the number of protons in the nucleus is increasing. This increase in the number of protons result in a greater pull on the electrons from the nucleus, causing the atomic size to decrease. So that's why the atomic size will decrease from left to right because you're increasing that positive charge in the nucleus, and that will pull more closer the electrons to the nucleus when you're going from left to right in the same period. Factor number two is that as you move down a column in the periodic table, the atomic size increases. As you move down a column in the periodic table, the highest principal quantum number n increases. Since the size of an orbital increases with increasing principal quantum number, the electrons that occupy the outermost orbitals are farther than from the nucleus as you move down a column. So here we have basically a representation of that periodic property of the atomic size. From you going from left to right, okay, the atomic size is decreasing because here we have in this in the same number principal number, okay, we're number two, and as you go from left to right, the number of protons in the nucleus is increasing. So you're increasing that positive charge in the nuclei. So those protons will pull more those electrons close to the nuclei, causing that atomic size to decrease from left to right. But when you're going from top to the bottom in a family, okay, because you're increasing the principal number, well, the atomic size also will increase when you're going from the first row to the row number 6. Another periodic property that we can find is the ionization energy, which is the energy required to remove an electron from the atom in the gaseous state. Ionization energy increases as you move to the right across a period and decreases as you move down a column in a periodic table. So here we have a trend for the ionization energy. So remember that the ionization energy is the energy required to remove an electron. So as we mentioned before, lithium will lose that electron pretty easy because if they lose that electron, they will have the same configuration as helium. The same thing with sodium. If sodium release that electron, will become electronic configuration of neon. So for them, it's really easy to give that electron. But as we move into the right, this one requires to what? To gain electrons. So it's really hard for them to release an electron. So that's why the energy, okay, to remove those electrons are increasing where we are going from the left to right. The ionization energy increase from left to right. And decreases when you go from the top to the bottom. Why? Because now the atomic size, okay, the atomic size of each atom is increasing. So it's more easy to remove an electron from the outermost shell of an atom with a principal number of 6 because that electron is pretty far away from the nucleus as one from level number 2. Because if you are in the period number 2 here, that electron is pretty close, okay, as compared to the one in cesium that is in 6s, sorry. So if you want to remove that electron, it's more easy to remove from a 6s than from a 2s. So that's why the ionization energy decreases going down because it's more hard to remove an electron from this part than from the bottom of the periodic table. So that's why the ionization energy increases from left to right and also decreases from the top to the bottom. The last periodic property that we will discuss here in this model is the metallic character. Metals tend to lose electrons in their chemical reactions, while nonmetals tend to gain electrons. As you move across a period in the periodic table, ionization energy increases, which means that electrons are less likely to be lost in chemical reactions. Metallic character decreases as you move to the right across a period and increases as you move down a column in the periodic table. So the metallic character will decrease when you go from left to right, and as we mentioned before, all the metals are in the left side of the periodic table and the nonmetals in the right side. So that's why the metallic character will decrease from left to right, and also it will increase as you move down, okay, a family, okay, or a column in the periodic table. So the light is a form of electromagnetic radiation, exhibit both wave-like and particle-like behavior. Particles of light are called photons. The Bohr model is the emission spectrum of hydrogen can be explained by using this model for the hydrogen atom. Each orbit is specified by a quantum number n, which also specifies the orbit's energy. The quantum mechanical model describes electron orbitals, which are electron probability maps that show the relative probability of finding an electron in various places surrounding the atomic nucleus. An electron configuration indicates which orbitals are occupied for a particular atom. Orbitals are filled in order of increasing energy and obey the Pauli exclusion principle. Each orbital can hold a maximum of 2 electrons with opposing spins. And Hahn rule, electrons occupy orbitals of identical energy singly before pairing. So we need to remember those two rules are really, really important. The periodic table are elements within the same column of the periodic table have similar other electron configurations and the same number of valence electrons, and therefore have similar chemical properties. Okay, because of that, they have similar chemical properties. The periodic table is divisible into 4 different blocks: the S block, the P block, the D block, and the F block, in which particular sublevels are filled. As you move across the period to the right in the periodic table, atomic size decreases, ionization energy increases, and metallic character decreases. As you move down a column in the periodic table, atomic size increases, ionization energy decreases, and metallic character increases. So this will be all for Chapter 9, Electrons in Atoms and the Periodic Table.